So far what we did is that we discussed the first type of reaction of your carbonyl and pi star reactivity. We studied the cleavage reaction, in which we took our alpha cleavage 1, and we said that there are 3 types of ketones which can do this cleavage reactions. One is your saturated cyclic ketone, another should be like saturated acyclic ketone. Then we took like ketone which has a beta hydrogen. Then we studied the chemistry. After finishing alpha cleavage reaction, then we went and we studied about the beta cleavage reaction. So, these are the cleavage reactions so far what we studied on first class of reactions. Today what we are going to do is that today we are going to study the another important type class of reaction of carbonyl reactivity, that is your hydrogen abstraction. So, initially we will try to discuss on intramolecular hydrogen abstraction, later on we will work on intermolecular hydrogen abstraction. So, today class we will be focusing on intramolecular hydrogen abstraction of your n pi star reactivity. Okay. This is your second class of second type of reaction which you see in carbonyl chemistry. So, I will take an example. This type of chemistry where you can see a ketone system or a carbonyl compound which has an with the gamma carbon should have an hydrogen. Okay. When a gamma carbon has an hydrogen, then you see most of the time this intramolecular hydrogen abstraction reaction dominantly happening. Okay. So, I will take a carbonyl system which is an aromatic. So, this is my alpha, my beta, this is my beta carbon where I can have hydrogen. So, I have considered a type of system which is an aromatic, okay, aromatic ketone. So, once I fertilize this, you know that what happens, it goes to S1, right. Then you say that it goes to its triplet state, because it undergoes an intersystem crossing, you go to a triplet. So, I am just writing the structure. A bit. I call this as T1, my triplet state, right. Now, what this can do? You have an alkoxy type of radical, and we study this alkoxy radical can abstract an hydrogen atom. Okay. So, it abstracts an hydrogen atom from my gamma carbon. So, it can abstract this hydrogen. If this abstracts the hydrogen, then what I am going to get? So, what is this? It is 1,4 diradical. I want you to start now looking into radical systems. Okay. So, that will be, once you know it is 1,5 or 1,4 or 1,3, then you know their chemistry, because you have studied their chemistry. So, the initially what photochemistry you are talking about, you have a carbonyl compound which has a hydrogen in the gamma carbon, you fertilize that, it goes to excited singlet, from there it undergoes a proper intersystem crossing to triplet. Then what happens? I have a O dot, it is like an alkoxy radical abstracting an hydrogen from the gamma carbon to give me a 1,4 diradical. This happens in light. Okay, this is a proper photochemical process, or you can call as a primary process. Clear? Now, we will see what happens to your 1,4 diradical, what this 1,4 diradical can do. So, it is a 1,4 diradical. What we have studied, what 1,4 diradical can do? We have studied, right, so far. One, it undergoes a nice cyclization, right. You can see a cyclization of 1,4 diradical. I don't get a cyclic system. Another what you observe 1,4 diradical can do is your beta cleavage, right. You can do this cleavage. Then what you get? You get a enol and an alkene, and this you know it can't atomerize to give me my acetophenone, right. You can get a beta cleavage reaction. So, one more it does, what it does, which we have not seen so far. You can see reversal of your hydrogen. This hydrogen again can get back to your radical, from where it came it can reverse back. Okay. You can see reversal of hydrogen. If it happens, then I might end up with the again back my starting material. So, we can see three reactions, one is cyclization, beta cleavage reaction, another is reversal of hydrogen. How we know that it undergoes a reversal of hydrogen? Any idea? Because again I am getting the starting material. So, how can I say that this reaction is happening? Deuterium labeling, I have again CH 2 CHD, then again it reverse, again I will be getting only deuterium. Why I am stressing this? Yeah, very good. Why I am stressing this? You have to understand this is a radical chemistry. Okay, you are talking about 1,4 diradical. So, all your processes goes by radical. So, if I have a chiral carbon, then what happens? For example, I am taking an optically active R form or something like that. Then once the reversal happens, you might end up with an S. Okay. So, I will be ending with a racemic solution. I am taking an optically active compound, then I will be getting a racemic. If that happens, then I know that reversal of hydrogen takes place. Clear? So, that way you can find out. Then this reaction, beta cleavage reaction, okay. Your ketone forming 1,4 diradical and 1,4 diradical, then undergoing a beta cleavage reaction. What you call this? It is a famous reaction. It is your Norrish type 2. We have seen Norrish type 1, which is your alpha cleavage. There we have studied about Norrish type 1. In forming 1,4 diradical followed by a beta cleavage reaction, it is Norrish type 2 reaction. Okay. See, in this chemistry, when you take a system where you have an gamma carbon, the cyclization and your beta cleavage reaction will be more dominating. So, you have to find out which will be, in one case you get cyclic product, in other case you might end up Norrish type 2 reaction. Okay. We have to figure out that. Now, we will see little bit about the orbital picture of this 1,4 diradical. Okay. See, once we finish intramolecular hydrogen abstraction, we normally do the problems. We will do this in this class, lot of problems, we have a number of problems. Before getting into problems, we should know some fact of these reactions. Okay. First, you should know why this 1,4 diradical gives a cyclic product and why it gives Norrish type 2. Can we understand little bit with the orbital picture? Then you should ask like whether this ketones, all the ketones goes only by triplet excited state. If I take an aliphatic ketone, then whether it goes by triplet excited or it goes by singlet or it goes by both, that you can that you have to understand. Then you have to say like if gamma carbon does not have any hydrogen, then whether it will take beta. So, how facile to take an gamma carbon, that you should try to understand. Then if you have a structures, whether structures can determine my reactivity, depending upon the structure can I get more Norrish type 2 reaction or like a cyclization. If we can know this fact little bit, then we can go and work on the problems. Clear? See, I am just taking the one earlier 1,4 diradical. So, I will just try to write the some small orbital picture of this and see how it happens. Like if I can write an orbital for this guy, C, I can have a phenyl. Right now, I am writing R for that. I can have an OH, then I can have a carbon system. This is one way of drawing your 1,4 diradical. Okay. If this is in this fashion, okay, then it can do your cyclization reaction nicely. It can do cyclization. You can get a cyclization product. But the same thing I can draw in other way also. Done this. Can you think of drawing it in another way? Perpendicular. Can you draw? Draw it in a book. if it, so it can also be like this, your 1,4 diradical, right. So, you can have a way like this where you have earlier drawn, where both the planes are same, it allows to cyclize. If it is not, then if it is in this fashion, then it is not going to allow you to cyclize, right. Then it happens your Norris type 2 reaction. Clear. So, I just seeing simple orbital picture, we can think why it has an option of doing a cyclization as well as Norris type 2 reaction. Okay. Done. So, now we will ask like a second question, like where does Norris type 2 reaction goes only by triplet state? It is not like that. See, it depends upon what ketone you are dealing with. If you are talking with an aromatic ketone, okay, it has different excited state. If you are talking with an aliphatic ketone, then its excited state is different. Okay. So, first what we will take, we take an aromatic ketone, which we are dealing right now, and in parallel we will take an aliphatic ketone. See, if I try to understand this with respect to your excited energy levels, for example, I have an S0, okay, and I have an S1. So, where I write my T1, I write like below this. See, the gap between your S1 and T1 in the case of aromatic ketone, it is very small compared to your aliphatic ketone. If you take an aliphatic ketone, S0, S1, this energy gap, the case of aromatic ketone is very small. When you take an aliphatic ketone, comparatively it is large, right. So, if a molecule gets excited to S1 in the case of an aromatic ketone, it immediately undergoes intersystem crossing, okay, and the rate it undergoes is 10 to the power of 12 second inverse. Okay. In the case of aliphatic ketone, is 10 to the power of 8 second inverse. So, now you know, okay, when I take an aromatic ketone, if I excite it, it goes to S1 and immediately it undergoes a very good intersystem crossing to give me T1. So, if I see the photochemistry should be coming from my T1 excited state, but in the case of aliphatic ketone, it goes to S1. Now, it can do an intersystem crossing to T1, or it can carry out a reaction from the S1 itself. So, in the case of aliphatic ketone, you will get photochemistry happening both from S1 and T1, clear. So, if I say this, I will say S1, sorry, photolysis, I will get S1, which then gives me T1, and that gives me 1,4 diradical, the case of an aromatic ketone. If it is an aliphatic ketone, I will say it will be S1 or T1, which will be giving me 1,4 diradical. because of your intercrystal, you see the rate, it is 10 to the power of 12 second inverse, it is 10 to the power of 8. So, once it reaches S1, it can do the chemistry Norris type 2 or cyclization to give me 1,4 diradical, or it can intersystem cross to T1. Clear? The third point which we will discuss is that the stereochemistry of your hydrogen abstraction. We will take the same ketone, see how we can discuss this. So, I am just writing the T1 right now. See, these things what we are doing will be helpful when you do the problem. Okay, just understand these things. Now, this O dot has to abstract an hydrogen from the gamma, okay, but it has a condition to do this. The carbonyl and your gamma carbon with an hydrogen should be in plane. Okay. If they are not in plane, if your carbonyl and the gamma carbon should be always in plane. If they are not in plane, they do not do this hydrogen abstraction. You will see a lot of examples where you have 2 gamma carbons, okay, then it preferably it takes a carbon which is in plane to your carbonyl system. That is very important condition. Okay. If you just see, I have this is my radical, right, and this is, for example, this is my gamma carbon. So, they should be always in plane. Okay. If it is not in plane, nothing happens. So, that condition you should always remember, very important condition. See, I will give you an example where you will really appreciate it, why this concept is important. I can write an epimer to this, right. You have now 2 systems like this. Okay. One is in the axial and another is your equatorial part. Now, think which carbonyl will do the 1,4 diradical, that is your intramolecular hydrogen abstraction. I have A, I have B, which will do, which you think is in plane. So, it has to see alpha, beta, gamma, it has to take this hydrogen in both the cases. So, it will take from A. You see your carbonyl and your this one will be always in plane, but in B it will be down, fine. So, if I take the A and photolyze, I end up with Norris type 2 reaction, but if I take B and photolyze, I end up with Norris type 1 reaction. Since this guy cannot abstract an hydrogen, it does an alpha cleavage. So, it does not mean that it will not do any chemistry. Okay. It does not do intramolecular hydrogen abstraction, but alpha cleavage is dominant. So, you can see Norris type 1 reaction happening from there. in this case it is Norris type 2. That is why I said the carbonyl should be in plane to the gamma carbon, the hydrogen, otherwise your chemistry, because most of the example we will be working like this. We will have a system where you have like gamma carbons available, but it tries to take only the hydrogen which is in plane, otherwise it does not do. So, keep that in mind. Okay. Then the third part. The another thing, whether substrate has any control across your cyclization or Norris type 2, whether substrate can control the reaction. Okay. For example, we will take the same example and see what happens. So, it might give me an, I am writing the direct T1. So, I get a 1,4 diradical, okay, on photolysis. So, this 1,4 diradical now have an option of doing cyclization or Norris type 2 reaction. Now, what I will take an example in which I have a AR carbonyl. I am substituting the alpha carbon. Taking a one set of carbonyl where I am substituting the alpha. Same way I am taking the same carbonyl I am substituting by an R there. So, I am substituting basically the gamma carbon. So, I have a same system. In one carbonyl system, I have substituted the alpha carbon. In another carbonyl set of molecules, I have substituted the gamma carbon. Now, you say like if I take the carbonyl, okay, this one, and excite, I know that it will abstract an hydrogen from here. So, what radical I am generating? If I abstract this CO dot abstracts an hydrogen from my carbon, then I am generating a type of primary radical. Okay. If I go to this secondary radical, when I go, I am generating tertiary radical. So, how the reaction should be? So, it should be faster, right? Yeah. Once I move towards, if I keep on substituting my gamma carbon, okay, then my Norris type 2 reaction will be dominating because of the stability of your radical formed. So, your gamma you are understanding. So, once I go down, so Norris type 2 will be dominating if my gamma carbon is more substituted. Now, other way around, if you come to this carbonyl system, okay, if I increase my alpha substitution, then my cyclization product will be dominating. Okay. So, gamma substitution, if I have seen any product where my gamma substitution is more, then I will prefer to do my Norris type 2 reaction, and cases where I see alpha is more substituted, then I prefer to do my cyclization. So, structure also has some determining fact over the product formation. This is all about the stability of a radical, okay? How fast the radical gets stabilized. Now, the another one is like why this gamma hydrogen abstraction should be faster, that you guys I think know. If I have a system like this, okay, if I am going to abstract this hydrogen, what happens? I am basically trying to make a 6-member transition state, right. So, that is why this molecule prefer to abstract a hydrogen from the gamma carbon, because of their 6-member transition state. It does not mean that this is not going to abstract other hydrogens, okay. It will try to do other hydrogen abstraction. If for example, my gamma carbon does not have any hydrogen, okay, then it will be abstracting my beta hydrogen. Even you form a 5-member transition, but anyhow it will abstract the beta hydrogen. Only the rate of the reaction will be very less, okay. So, if you say like alpha abstracting from alpha will be the least one, then comes your beta, then comes your gamma. So, gamma abstraction will be very fast because of your 6-member transition state. And there are many other reactions where it starts to abstract from 7-membered, 8-membered, from 7 like 1, 2, 3, 4 carbon, 5 distance also it starts to abstracting. We will see that examples also. It is not like it only the favorable is from the gamma carbon. But one thing you have to remember now, if I give an example, you have to now understand whether it does alpha cleavage, okay. It does not need to directly get into intramolecular hydrogen abstraction. You should first think whether my compound can do alpha intramolecular hydrogen abstraction or alpha cleavage. That also you have to notice now, because you are now seeing the second reaction, right. Okay. So, this is more about the aspects of Norris type 2 reactions. Okay. Now, what we will do? We will try to do some examples and we figure it out how it works. Oh, sorry. Okay, it should be other way around. Okay, thanks. So, what we studied so far? We studied that depends upon your ketone, okay, the excited state. If it is an aromatic, then I will go for a triplet. If it is an aliphatic, it comes from both singlet and triplet. Then we said that the hydrogen which the alkoxy radical or your carbonyl should be abstract should be in plane. Then we said that if the substitution on your gamma carbon increases, then Norris type 2 reactions dominates. So, we should understand all these points when we do the problems. Okay. We will do the first example now. Once we take this and photolize, now I know it is an aromatic ketone. Okay. So, I will say it is S1, then I can say it undergoes a nice intersystem crossing to my T1. Okay. So, this step is very important because that is the photochemistry step. Then from T1 what happens? If you look, I have an alpha, this is alpha, I have a beta, I have a gamma, right. So, my carbonyl can abstract this, my alkoxy radical once it excites can abstract this hydrogen. Right. So, I can write my then so you get this 1,4 diradical, nice 1,4 diradical. So, this is the photochemical process. Now, we should think what this 1,4 diradical is going to do. Okay, what it can now try to do? So, you can think about cyclization, right? Do you want to do a cyclization on this? You are going to make a very strained ring, yes. So, I can do a beta cleavage then. If I do a beta cleavage, a system like that. Just first write with respect to structure, then we can find out the, then you know it has this. So, I got this. So, if I want to write it in properly, right. So, see if you see in this angle does not look to be a type of a stable molecule, but actually it is a 6-member ring. Okay. That is why this chemistry prefers to go towards Norrish type 2. Okay. This is a very good example for your Norrish type 2 reaction. Here you get predominantly only Norrish type 2 product. Any doubt? Okay. So, we will then do our second example. Okay. nice type of not boring structures, like we should, it is always nice to work on this type of bicyclosystems. Okay. Now, what happens if I photolyze this? What happens? It goes to S1, but the chemistry can also happen from the S1. Okay. That is why I said, like, it is a type of an aliphatic now. Okay. It can happen from S1 or T1, then you write the product. So, from where it can abstract now? Alpha, beta, and you have a gamma. Yeah, this is also gamma, but both are same if you are going to abstract from any direction. So, you get a diradical 1, 2, 3, 4, right. You can carry over by yourself, just for clarity I am taking this page. So, what reaction, what you are going to expect now? So, I have 1 4 diradical. So, you cyclization or Norris type 2? Why? Huh? Yeah. So, it is highly strained double bond, which so you will prefer to do by cyclization. Okay. You just write both the products and see like how it looks like. This is your cyclization. Sometimes it is better that you write both the products and then you decide like which is going to dominate or not. Like. So, in this example you can nicely see like you do not want a double bond or an alkene in the bridge side, because it will be really highly strained one. So, this is highly strained. So, molecule does not want to do this. So, you get a nice cyclization product. See, first example we took where we got only Norris type 2 happening, no cyclization. In this example you can see we predominantly get your cyclization product, not your Norris type 2. See, it depends, that is why I say substrate has more to do, deciding what type of chemistry you are working on.
So, previous example is also aromatic ketone.
No, previous example was aromatic ketone. It was a phenyl, right?
No, not phenyl. That only
example 1. Yeah, it's a phenyl. Okay, it's a phenyl one. This is your observing unit, right? Because this will have your absorption, not this part. That is why I took that one. Okay, clear. That is why I said that it undergoes intersystem crossing and goes to triplet. There are many cases in aliphatic also you can see Norris type 2 happening. Okay. So, it is not that. So, you have to find out both the reaction and see with respect to product also. Yeah, once you do examples, then you will easily figure it out, and you have to understand the radical stability also. Once you are getting a 1,4 diradical, then you should know whether these radicals are stable, and so you have to take most of this into account. But once you do keep on doing examples, you will just find it out, nothing wrong in it. So, we will take another good example. We are trying to take a very strained ring, okay, and see what the idea whether it can photolize. Then I can say always it is S1, since it is again a type of aromatic ketone. Okay, I am saying that it will undergo an intersystem crossing to give me my T1. Okay. Now, your thing is little bit easier, na? Because here you do not have gamma at. So, it is alpha, beta, gamma. So, I have to, so sorry, alpha, beta. No, I think I am with an extra, yeah, yeah, fine. Beta, gamma. So, this can abstract now the hydrogen from here. So, I get a diradical. Okay. This I will try the structure of diradical again, but you can proceed by yourself. What will happen in this example? What you are going to try to do? Are you going to cyclize, or you want to carry out your Norris type 2? See, that is what, if you are like that, it is better to draw the structure. Once you draw the structure, then you will know. Okay. See, if this ring is not there, then you would have been thinking about doing your cyclization. Now, you are thinking like 3, 4 followed by a 4. Okay. If you think like this, see, if I do not have this bond, then it will be a 6, 4, that is okay. Now, you are thinking of drawing a system 3, 4 and 4, yeah, 3, 5, 4, which is not like that much possible, okay, with this alkenes and everything. So, that is why you are not going to prefer cyclization. In this case, again it goes Norris type 2 reaction. See, now you can see how molecules are becoming like how much it can see whether it wants to make one cyclization or you want to do an Norris type 2 reaction. Clear with these 3 examples. Now we can grab another example. See, every example teaches you something. Okay, first example may you learn what is cyclization, second may you learned how it goes Norris type 2. This example also teaches you something different. You have to think why I am like it is an alpha, beta, okay, then I have a gamma, fine, but you have a double bond. So, you have to just understand now what we are going to, what this really going to tell you. So, you have to ask several questions now, like whether I can abstract an hydrogen here or I can abstract an hydrogen, oh sorry, yeah, hydrogen from here, no, not possible, it is only from here. If I generate a radical, then what that radical is called? Allylic radical. So, allylic radical what they prefer to do? Allylic radical prefers to do because it is type of a stable type of radical. So, it likes to cyclize. Fine. So, with that knowledge we will do this example, we will have a break, okay? Then we will come back and start doing this example. Clear?